Okay, we start section 2.1 and we're going to define some angles and their measure. And basically I'm just going to show you some of the visuals that go with this. So when we have a array, the vertex is here and basically it's a straight line that ends in an arrow. Okay, so it continues in a direction, in one direction. Another thing that we're going to talk about is going to be if we're given a vertex, and this is always our initial side, the terminal side is going to be where the angle is stopped. So this is where it starts. We move in a counterclockwise rotation. This gives us a positive angle, alpha. So that's going to be our standard location. On this particular one over here, if my initial side is this arrow, okay, and I move all the way around counterclockwise, it's a positive angle, and it just goes more than one revolution all the way around. So that's angle lambda. We'll have that kind of situation. All still positive angles. Now, if I start at my initial side right here, and I go in a, let me see if I can move this down a little bit, clockwise rotation. So if I start at my initial side and I go clockwise, I have a negative angle. So beta is a negative angle. So those are just the orientation of a positive angle, which is basically counterclockwise rotation, and a negative angle, which is a clockwise rotation. Okay, the next thing we're going to talk about is quadrants. So angles lie in which quadrant. So for example, if I had my coordinate system, this is quadrant 1, this would be quadrant 2, this is quadrant 3, and this is quadrant 4. So for example, if I look at this first one up here, which you can draw a rough sketch of it, which angle does theta lie in? Which quadrant does theta lie in? Theta lies in, so for this one we'll say theta lies in quadrant 2. Okay. This next example, if I ask you what quadrant does theta lie in, what do you tell me? It lands exactly on it. So for example, this is called theta is a quadrantal angle. So this has a special name for it. So it's a quadrantal angle, and that's because it lies exactly on the quadrant. So even if it would have landed on this line right here, it would have been quadrantal, as well as if the terminal side would have landed here, would have been quadrantal here, or back at the initial, if the terminal initial were on the same, it would be quadrantal. Okay, so this is a special case. We look at this last example over here, and if I ask you what quadrant does angle theta lie in, we'll say theta lies in quadrant what? Good, quadrant 4. Quadrant 4. Okay, so locations, and like I said, this is the one that has a special name. It's a special case. Terminal initial side is here. Terminal side lands on an axis. Okay, in this next part, we're going to just practice drawing an angle, and I put about 4 examples up here that we're going to work with. Let me make that a little neater. Okay, keep in mind that if I start here, let me put it in a different color, my initial side here, and I go counterclockwise all the way around, that's considered one revolution, which is how many degrees? That's 360 degrees. Right? A circle, 360 degrees. So start at the initial, go counterclockwise all the way around, consider one revolution. Now, excuse me, with that in mind, we're going to start at our initial side. So this is our initial side for 45 degrees. Okay, and we want to go approximately 45 degrees. Now, if you knew these are 90, 180, 270. Degrees. So we're just going to do an approximate. We're not perfect here, and these are rough sketches. So approximately 45 degrees would be halfway here. So this is angle that is 45 degrees. Angle theta, 45 degrees. Okay, terminal side ends there. For this next one, negative 90, instead of going in counterclockwise because it's a negative angle, we're going to start at our initial side and we're going to go in this direction, right? So this is 90 degrees, negative 90 degrees. Okay, positive 225 means my initials here, and I'm going to go, that's 180, so 225 I'm going to estimate to be over here. Okay, so 225 degrees is going to be my angle. It's a positive angle. Now, what do you think we're going to need to do to get 405? Clearly go around once, right? More than once. Well, how much extra after? 405 minus 360 is what? So 45 degrees. So basically I'm going to go all the way around one revolution. So if here's my initial, I'm going to go all the way around. That's 360, and then I need to go another 45 degrees. So if I approximated that roughly all the way back around, that would represent the terminal side for 405 degrees. So the biggest thing is remember negative angles go in the opposite direction. Okay, our next concept is going to be radians. Standard unit of angular measure. An angle's measurement in radians is numerically equal to the length of a corresponding arc of a unit circle. Also, 1 radian is about 57, a little under 57.3 degrees, but you can see that where this is length R, this is length R, also the arc length on this side is R, so that's what represents 1 radian. Okay, next we're going to look at arc length, and for a circle of radius r, a central angle of theta radians subtends an arc whose length is given by formula S is equal to r theta, where this is your radians and this is your angle theta. We're going to work with some examples solving for different values here. Okay, our first example, they're asking us to find the length of the arc, which is denoted by S. When they give us the radians, the radius is 4, and the central angle is 0.5 radians. So basically we're going to plug it into our formula and solve. Okay, so we write our formula. We're solving for S. Oops. S is equal to radius was given. Radius is 4. Theta was given to us. Central angle theta 0.5. This must be in radians. So later if they gave it to you in a different maybe degrees, we'd have to convert it to radians first to then use the formula. But we can talk about that a little more later. So 4 times 0.5 is just going to be 2 meters. For this next example, I gave you an abbreviated version. It's the same word problem as the last one, but this is all your given information. So your radius, your radian, and it's asking you for S. So plug that in the formula and solve. Okay, so basically you plug in the given information and solve for S. Multiply that. Make sure this looks like a 10. 10 times a half, which is just 5. Okay, I'm going to give you another one too. Okay, this next problem, I give you your theta, and this time we know S, but we're looking for the radius. So we start with our formula. We plug in all our given information, so I know that S is 2, R I don't know, my theta is 1/3. If I'm solving this for R, we're going to multiply by the reciprocal, which is 3, so whatever you do to one side, you do to the other, and you would get 6 is equal to R. So let's say 6. Okay, we'll do this one more time. This time we're given the radius, we're given the arc length when we want to know angle theta. Okay, so let's plug in all our given information. So S is going to be 3. R is 5. Theta is what we're looking for. Now we want to treat theta as a variable, so if I want to get theta by itself, I would just simply divide both sides by 5. And 3/5 is equal to theta, which if I wrote 3/5 as a decimal, it's going to be approximately 0.6 radians.